All right. Welcome everyone to this public lecture by Andrew Hassell as part of the MSI public lecture and of the AMSI Summer School 2024. So it's my great pleasure today to introduce my colleague and good friend Andrew Hassell. He has done his PhD at MIT and did a postdoc afterwards at Stanford. Among the many honors that he had, he been elected to the Australian Academy of Sciences in 2015. He was a Laureate Fellow, and he's now a fellow, an Australian Laureate Fellow. So he's an expert in microlocal analysis, which he's going to tell us a little bit about today. And there are connections to physics, partial differential equations, which is also part of the topics today. So today's lecture is going to be on scattering theory, or in less technical jargon, focusing on the very big picture. Let's welcome Andrew to this. Thank you.
Thank you, Paul. I hope you can hear me well enough at the back. Is that good? Yeah. Yeah, I have two immunocompromised family members, so I need to be extremely cautious with masking and so on. Yeah, so let's get straight into it. So we'll start with classical scattering. Firstly, just in one dimension. So this is really quite simple. Imagine an idealized marble, frictionless, moving along an infinite one-dimensional track. And the one-dimensional track can have hills and valleys, but is perfectly flat outside some bounded region, say LR. Then what happens? All right, so we can think of this as a one-dimensional landscape with height function V. Well, in this case, high school physics can solve the problem for us. So we know that we have conservation of energy, and we can write that in this form. So the kinetic energy plus the potential energy is equal to the total energy. Now I'm writing V for the potential energy. Technically, I'm making some identification between the height and the potential energy, but they're proportional. And I'm just ignoring constant there. And this equation tells us some useful facts. Firstly, the marble cannot reach a position where V is greater than E, because then we can't solve this equation. We'd have to V squared negative, which is impossible. Secondly, if the marble passes through the interaction region, so by the way, this region between L and R where V is not zero, I'll call the interaction region. If the marble passes through the interaction region, then it will have the same velocity after as it did before. And that's direct from this equation. So we set V equals 0, and we find that we can determine V in terms of E. So in fact, there are three possibilities, depending on what the value of E is and what the shape of V is. The first one, if V of X is less than E everywhere, then the marble will travel from minus infinity to plus infinity with the same velocity before as after. So in this picture, here we have a value of E, which is on this energy axis, which is greater than the maximum of V. So the marble will always have positive velocity. It'll travel through the interaction region. However, if there is a value of X where V of X is bigger than E, then the marble will return, starting from minus infinity, it will return to minus infinity. That's illustrated by this. So if the value of E is E lower star here, which is smaller than the maximum value of V, then at some point, the marble will get to a place where V of X is equal to this E lower star. And then the velocity is 0. And what the marble does is it turns around and goes back. Then, as you'll notice, there's an intermediate case. If the maximum value of V is exactly E, and assuming V is smooth enough, then this idealized marble will actually be trapped. So it will reach the top, the top of the hill, if you like, but at zero velocity, and there it will stay. That's a very unstable situation, and in practice unlikely to be observed, but that's a theoretical possibility. Okay, so one-dimensional scattering is quite simple. Slightly more interesting is two-dimensional classical scattering. So now we're still rolling a marble, but this time on a plane. And the plane is flat most of the time, but in some bounded region, it has some topography. So here's a little hill in the middle of this plane. There could be many hills and valleys and so on. And once again, we want to think about the initial state and the final state. So what we get here is that as long as it's traveling in a perfectly flat part of the plane, then it's just straight line motion. That's easy. We can describe it explicitly. And so we think about this particle coming, or this marble coming in from infinity. So we'll have a definite, it'll travel along a straight line. And so how can we parameterize that straight line? Well, a straight line has a direction. And then of all those lines in a given direction, well, that's a one-dimensional family of lines. One of them passes through the origin, and the others can be parameterized by the distance from that line. So this A is an offset. So the initial theta I is the initial direction, AI is the offset. It's the distance between that line and the parallel line that passes through the origin. Then something complicated happens as marble interacts with this potential function. But we come out again, and then there'll be a final direction and a final offset. So the classical scattering map is the map. It takes the initial direction and offset, the final direction offset. Okay, so here's an example to think about. An interesting case is where the potential is rotationally symmetric. So that is in polar coordinates, it depends only on the r coordinate and not on theta. Then a little thought shows that the classical scattering map takes this form, special simple form. So it will take theta and A. Well, first of all, the A is preserved. So the final A is equal to the initial A. So that offset is the same. Then what happens? What's the final theta coordinate? Well, it's the initial coordinate plus a difference, but that depends only on A, not on theta. So it actually takes a little bit of thought to see that it's that form. That's the case. And so in this case, where we have a rotationally symmetric V, the classical scattering is determined by one function of one variable. It's called the scattering angle. It's the angular deflection experienced by trajectories that emerge, that come in from infinity with A. So we've just seen two examples of what I'm calling the general philosophy of scattering theory, which is that in many cases, in many dynamical systems, we have the following scenario. We have an initial simple dynamics. So for time very negative, the dynamics are simple, can be described explicitly, for example, straight line motion. And similarly, there's another asymptotic region when time is very large. But in between, there's some complex dynamics, which is caused by the, say, the marble interacting with this potential, which could be complicated. And that's the interaction region. So the philosophy of scattering theory is to relate the simple before and after dynamics without worrying too much about the complexities of what happens in between. Yeah, so there's a number of ways in which one can do that. In fact, we've already seen one way to do that, which is the conservation law. In the case of the one-dimensional marble, the conservation of energy was actually enough to relate the before and after states. Well, I'm actually more interested in quantum scattering than classical scattering. I'll move to quantum scattering. And so instead of a marble or classical particle, we're going to consider a quantum particle or wave function. So a quantum particle is not localized to a particular place, but rather there's a kind of probability distribution that tells you how likely a particle is to be at a particular place. So it's determined by a wave function, which I'll call u of x. And this is wave function, we'll soon see, is complex value. And actually the probability density will be the modulus of u squared. So before, go back to this equation 1, we had this energy equation for the marble. So kinetic energy plus potential energy equals total energy. Well, similarly in quantum mechanics, we actually have the same equation in a sense, but the quantum mechanical analogues. So the kinetic energy is now this term here. It's so this is actually one dimension to start with. This u is a function of a one-dimensional parameter x. And this kinetic energy term involves the second derivative of u. The potential energy term is, before it was just v, the potential v, but now it's v of x times u of x. And this should be the total energy, which is E times u of x. So this is a case where we have a quantum particle of a definite energy E. So that's the equation, Schrodinger's equation. And well, we can analyze this. So first of all, we look at the simple region, the asymptotic regions, where v is 0. So I'm thinking of v as looking as it did before. So think of v as some sort of function like this. Okay, it's one dimension, it's non-zero except on some interval LR. So in the asymptotic region, v is 0, and then we have this equation. So h bar is Planck's constant, m is the mass. I'm not actually, being a mathematician, I'm not actually that bothered by constants. They don't trouble me too much, but I've put some of them in. Anyway, so it's minus a constant times the second derivative of u is E times u. And that, of course, is a rather simple equation that we know how to solve. In fact, high school students learn how to solve that. So the solution is a linear combination of sines and cosines. Okay, a nice linear equation. So the general solution is this two-dimensional subspace. And this factor here is just the square root of the constant that appears here. However, it's often more convenient to use complex exponentials. So recall that e to the I psi is cos psi plus I sine psi. And so we can equally well express it in terms of these two complex exponentials. And that's actually preferred in quantum mechanics because in quantum mechanics, a wave function like e to the I psi x represents a particle of definite momentum psi. So that's something very concrete in terms of its physical interpretation. So that's kind of like the marble moving at constant speed in the asymptotic region. Now, I just showed you the general solution, but let's take a particular solution. So let's just take one of these exponentials, say multiplied by some constant, in the right asymptotic region. So for x very large, where v is 0, we have this solution. And of course, this is an ODE. So if we have a solution in one region, we can solve the ODE for all x. Okay, so when v is complicated, we can't write it down explicitly, but we know there's a solution. And then we will pass through the interaction region and emerge in the left asymptotic region. And then, well, it must be one of the class of general solutions. This is the general solution, so it must be something like this. Okay, so we'll have both the plus I psi and the minus I psi exponential. Well, that's all very well, but we have these undetermined constants a, b, and c. So it turns out that they are not independent. We can derive an equation for a, b, and c. doing the following cunning calculation. So this will be the only time I actually do a calculation in this lecture, but we'll do it quite carefully. Okay. So we start with 0 equals this expression here. Now this line is complex conjugation, and it's a bit confusing, but this line here represents complex conjugation of this whole bracket. It's not just a dividing line between these two displays. So why is this? Well, what's in this first bracket is 0, because that's exactly Schrödinger's equation. Schrödinger's equation says that's 0. So I'm just taking this, writing 0 in this complicated way, multiplying it by u bar of x, still 0. And then I subtract u times what I had up here in this large bracket, but complex conjugated. So that's the complex conjugate of 0, which is 0. So this is definitely 0, this expression. But then we notice that we can write this as a derivative. So how does that work? Well, first of all, the v terms and the e terms cancel. When I took this combination, the v and the e terms cancel. Why? Because the v term on the first line is v times u bar. And then on the second line, we get minus u times v bar times u bar, but v is real, so v is v bar. So those two terms cancel, the e terms similarly cancel, and we're left with these second derivative terms which do not cancel. Now, if you look at this line, when we take the derivative, we notice that when we apply the derivative, so we have to use the product rule, of course, when we apply the derivative to the terms that all to the u prime terms, then that reproduces these second derivative terms. But there are two other terms, because we have to also apply this d by dx to the u factors. But then notice that when we do that, we get u bar prime minus u bar prime, which cancels out. So that verifies that identity. And you see, this is very nice now, because here I can apply the fundamental theorem of calculus and evaluate this integral between L and R. But L and R are in the asymptotic regions. So in that way, we kind of get rid of the interaction region and we're back in the asymptotic region. All right, so I'm not going to do the full calculation, but now what we're going to do, so we agreed that we had certain explicit forms for u both in the left and the right asymptotic region. Sorry. So here and here. So we just substitute these forms in for x greater than or equal to r and x less than or equal to L. And what we get actually is the following thing. We get 0, because we're calculating 0 here, remember, some constant times minus modulus of a squared plus the modulus of c squared minus the modulus of b squared. So these a, b, and c may be complex. So in fact, we get some sort of Pythagorean equation between a, b, and c here. And that actually has a very natural physical interpretation. So let's just see the physical interpretation. First of all, recall that we said that e to the I psi represented a particle with definite momentum psi. So this term actually represents, if you like, a continuous beam of particles with energy E coming towards the interaction region from the left. So illustrated here. The B term, similarly, this also applies for x less than or equal to L. So we're in the left asymptotic region, but now there's a switch in sign here. So this is a continuous beam of particles of the same energy, but moving to the left. And finally, the A term, well, this was in the right asymptotic region. So this is a continuous beam of particles with energy E moving away from the interaction region to the right. So as illustrated here. And so we can think of this as C being an incident beam. We fire some particles at a certain energy to this towards this potential, and then some of these particles are reflected back and some of them are transmitted, very much like the marble, which when we rolled it could either go back to minus infinity or to plus infinity. And the equation itself is a conservation of energy statement. So the sum of the energies of the particles that are reflected back and transmitted is equal to the energies of the particles that are incident. We can also think of this in terms of probability, because of course in quantum particles have probability of being in certain places. So if we think of a single particle being fired towards this interaction region, then it has probability a squared over c squared of being transmitted, or probability b squared over c squared to be reflected back. And so our equation is just the sum of those probabilities is of course 1. It's actually interesting that in quantum mechanics, as opposed to classical mechanics, the quantum particle can be transmitted even when the potential function is greater than the energy at some points. So there could be a potential barrier such that the marble would not be able to pass through, but the quantum particle can. That probability will be very small when the potential barrier, the maximum V, is much bigger than the energy. All right, so we've built up to quantum scattering now in 2 or more dimensions, the main topic of this talk. So what I say actually applies to more dimensions, in particular 3 dimensions, but just for expository reasons, it's convenient to stick to 2. So in 2 dimensions, Schrödinger's equation reads like this. So compared to what we had before in the 1-dimensional case, remember we had the kinetic energy term involved a second derivative of u, potential was V times u, and the total energy term is EU. So all that happens is in 2 dimensions, we get the second partials in both the x and the y directions. Or in other words, this is the Laplacian. So the second derivative gets replaced by the plus. All right, so now this is a partial differential equation instead of an ordinary differential equation. That makes it a little harder to solve, but we can still say a lot. Okay, so let's assume for simplicity, as we've done before, that V, this potential function V, is supported, say, in the ball centered at the origin with radius r. So it's particularly supported in a bounded region, and it's 0 outside. So in scattering theory, we need to understand the behavior first in the asymptotic region. What is the simple behavior in the asymptotic region? Okay, so, well, let's actually think about the case where V is identically 0. So what is the behavior in the asymptotic region? Well, in this case, we can solve the equation using the Fourier transform, and then we can use the stationary phase lemma to look at the asymptotics. So I'm not assuming you know what that means. That's why it's in red. It's kind of a warning. If you don't know what it means, just forget it. It won't affect your understanding of the rest of the lecture. So we'll use polar coordinates. And then what we find if we do this calculation is the following thing. So u as a function of r, distance to the origin, and theta, direction, has the following form. Well, first of all, there's an overall decaying factor. So this is r to a negative power. In dimension n, the power is minus n minus 1 over 2. I just write it in terms of general dimension. So of course, we're really looking at 2. So this is r to the minus 1/2. But notice that if n is 1, then this is r to the 0, which is 1. So we don't have a factor there. In fact, if r equals 1, then we just have what we had before. So that's a good check. This factor is just 1. Then we have the exponential moving to the left and the exponential moving to the right. But what happens in higher dimensions? Well, now we have r and theta. So that what we have is this is So we get these complex exponentials, and these can be thought of as radial waves or spherical waves, either moving outwards or inwards. But we also have an amplitude which depends on theta. And then, unlike in the one-dimensional case, those terms are the leading terms. So they're the biggest terms in an asymptotic expansion, but they're not exact. In one dimension, it's actually exact. But in more than one dimension, there are other terms, but they decay. So the next term decays is about 1 over r times the size of the main term. And so that's very small for larger r. And so that's not too complicated. And in fact, that asymptotic form can more or less be guessed by looking at pond ripples. So, the waves that we see or are easiest to observe in real life are pond ripples, which look like this. If we drop a stone into a pond, then we get this series of circular waves. They go outwards, and as they go outwards, the amplitude decreases. So that's exactly what's suggested here. And actually, another interesting point is if we drop an exactly spherical pebble vertically into a pond, then we'll have truly a rotational symmetric situation. But suppose we throw a long elliptical stone into a pond, then these waves will still be spherical, at least asymptotically spherical, but the amplitude will depend on direction. So the amplitude, the height of the wave will be bigger in some directions, bigger on the in the direction of the semi-minor axis than the semi-major axis, actually. So, oops. So just by looking at pond ripples and thinking about what we're seeing, we can almost guess the asymptotic form here. And then what we find is that we call the F minus the incoming data or the incoming amplitude, and the F plus the outgoing data or the outgoing amplitude. That's because the F plus is associated to the outgoing spherical wave and the F minus to the incoming spherical, I should say here, circular wave. And so, in fact, you can think of F minus as a free parameter. In fact, for every F minus, you can find a solution to Schrödinger's equation that looks like this. But then if you prescribe F minus, F plus is actually determined, which makes physical sense. If you determine what goes in, then that should determine what comes out. So, okay, that discussion was really about v equals 0, but even when v is non-zero, we still have this form of asymptotic. And what happens when v is 0, actually F minus is equal to F plus. So this looks like an unnecessarily complicated way to write this. But when v is non-zero, that's no longer true. So when we have a non-trivial potential, then the relation between F minus and F plus is not so simple. And in fact, we have something called the quantum scattering map, or sometimes called the scattering matrix, which by definition is the map that takes F minus and tells us F plus. So supposing we have a quantum mechanical situation, that is, we have a V, we have a potential function V. If you give me F minus, then I can try to find the solution to Schrödinger's equation that has this asymptotic with the given F minus here. And then it will also, so this will be this incoming circular wave. It will also have this outgoing circular wave with some F plus. And whatever that F plus is, well, it's determined by F minus. So we'll call it this operator S applied to F minus. This is the quantum scattering. So following the philosophy of focusing on the big picture, we're not so interested in solving exactly Schrödinger's equation. What we would like is to understand this scattering map. That is, if I tell you what goes in, you tell me what's going to come out. And of course, scattering theory, as the name implies, comes from particle physics, and that's what we do in particle physics, because the interaction region is of the order of something like 10 to the minus 11 meters, if you're studying an atom or small molecule. So, you can't go in there and kind of do measurements. All you can do is fire things in and see what comes out. So that's what physicists could do. So they wanted a mathematical theory that dealt with that situation. Yeah, so the scattering matrix is, from a certain point of view, the main topic of study when you look at scattering theory. And it links the incoming data F minus with the outgoing data F plus. And we can ask, what sort of properties does it have? Well, one property it has is the following thing. It preserves the squared 2 norm squared of F minus and F plus. And if you like, that's the analog in 2 dimensions of this one-dimensional equation that we saw before. And 10 is a very important equation, actually, from a mathematical point of view. But it tells us that S is actually a unitary operator. What's called a unitary operator. And what does that mean? Well, a unitary matrix, by definition, is a matrix satisfying this equation. UU star equals U star U. Star here indicates the conjugate transpose of the matrix is equal to the identity. So a simple example is a 2 by 2 rotation matrix. That is a unitary matrix. If we take this star of this matrix, well, that's the conjugate transpose, but it's got real entries, so just the transpose. So if you take the transpose, you're really just swapping the sign of these 2 off-diagonal entries, and that's the rotation matrix for minus alpha. If we apply a rotation of alpha followed by a rotation of minus alpha, we get the identity. So that would verify this equation here. And unitary matrices have a lot of nice properties, and one of them is that they're diagonalizable in the sense that they have a complete set of eigenfunctions and eigenvalues. So if the eigenfunction is W and the eigenvalue is lambda, that means get a basis of W so that U of W is lambda times W. Okay, that's just the eigen vector equation. Now, having said that, and having told you that rotation matrices are examples, you might think those are in contradiction, because of course a rotation matrix takes any vector and moves it to a vector with a different direction. And this equation is saying that U of W has the same direction of W. So how can that be? And the answer is complex numbers. So the eigenvector is actually complex. So for a rotation matrix, we can easily solve the eigenvectors and eigenvalues, and here they are. And pleasingly, the eigenvalues are kind of what you would expect they might be. So, did I forget to say something earlier? Just a second. No, maybe not. Anyway, the eigenvalues are cos alpha plus or minus I sine alpha, or in other words, e to the plus or minus I alpha. So they're exactly the points on the unit circle that you get by rotating by angle alpha minus alpha. So that is a general fact about unitary matrices or even unitary operators. Their eigenvalues always lie on the unit circle. And that's a very powerful property. So they always have the form e to the I alpha for some real alpha. And this is even true for the scattering matrix S that we just talked about. So that's not a matrix, or if you can think of it though as a matrix, but it would have infinite rank. So it's an infinite dimensional operator. So it has infinitely many eigenvalues, but they are all on the unit circle. And even more than that, we can say that these eigenvalues are discrete except at the point 1. But of course, if you have infinitely many eigenvalues on the unit circle, then there has to be an accumulation. There could be lots of accumulation points. Every point could be an accumulation point. But actually, no, especially in this particular case of scattering matrices related to this two-dimensional Schrodinger equation we're talking about, the eigenvalues are discrete except at point 1. So it looks rather like on this picture. So we can identify individual eigenvalues around the unit circle. Picture in the complex plane now. This is the spectrum. And they accumulate at point 1. So physicists call actually alpha over 2 a phase shift if e to the I alpha is an eigenvalue, the scattering matrix. And they're directly relevant to physics because you can actually measure them in physics experiments via interferometry. So, of course, mathematically, we would also like to make statements about the spectrum of the scattering matrix. So what can we say? Well, we can say quite a lot in what's called the semi-classical limit, which is the limit as h bar tends to 0. This is a very important limit both in the mathematical physics and the mathematics literature, and has been extensively studied. But you might sort of say, what are you doing here? Planck's constant is just that, it's a constant. You can look up the value, 6 decimal places in your physics text. What does it mean to take that to 0? The answer is that yes, Planck's constant is a physical constant, but it has units. So what that means is if you look at a particular situation, if you have characteristic length scale, characteristic mass, characteristic time scale, and so on, in those characteristic scales, Planck's constant could be either large or small. For example, if you look at an atom, Planck's constant is quite large. But if you look at a macroscopic object and the kind of length scales that you deal with, then Planck's constant is very small in relative to that. So it does make sense to take a limit as h bar goes to 0. What can we say? Well, I'll present to you 2 results which were obtained within the last 10 years, part of my research. So the first is if V is rotationally symmetric. So V, written in polar coordinates, depends only on R. Then we can actually find asymptotics for the individual phase shifts, the individual eigenvalues of the scattering matrix. So the way that works is like this. So if you go back to the scattering angle, we return to earlier in the lecture, we talked about the scattering angle. That was related to classical scattering in 2 dimensions when you have a rotationally symmetric P. So we integrate that to get g of a. That's just what that g function is. And then, well, in this rotationally symmetric situation, the eigenfunctions of S are actually just the Fourier basis. So S acts on functions on the circle. Remember, f minus of theta to f plus of theta. So it acts on functions on the circle. The eigenfunctions are just the Fourier basis, and the corresponding eigenvalue we can calculate in the semi-classical limit like this. It's the x of e to the I over h bar g of k h bar. So that's for the k. So that's for the eigenfunction e to the I k theta. So k is the Fourier mode. H bar is Planck's constant. Notice this is on the unit circle. So it's e to the I times something real. And then the error is order of h bar. That approximation is actually classical, and the error estimate, in fact, seems to first been proved in some work with myself with Kirill Dachev, Jesse Gil-Redman, and Peter Humphreys about 10 years ago. So that's a nice situation, but in a sense, it's an easy situation because when you have a rotationally symmetric V, then you know the eigenfunctions. of the scattering matrix kind of for free. It's not actually telling you anything about the physics. It's just a general fact about rotational symmetry. So what happens when you don't assume rotational symmetry? Well, then it doesn't seem possible to say what individual phase shifts are, but we can still make statements about the asymptotic distribution of those phase shifts around the unit circle. So the following result was proved in 2015 by myself with Jesse Gold-Redman and Steve Zeldich. Well, I say theorem. I'm not actually going to tell you all the conditions of the theorem. They're slightly technical. Suppose that potential is only non-zero in a bounded region. Yeah, these two conditions. Okay, so one of them is a non-trapping condition. It says that classical trajectories will not be trapped. So if it comes in from minus infinity, it will go out to minus infinity. Then there's a more technical condition on the periodic orbits, which I won't go into. But what can we say? Well, so remember the eigenvalues are on the unit circle, but there's infinitely many of them. So we distinguish the ones that are close to zero from the ones that are not close to zero. And we can say that there's a finite number, which is about c times 1 over 2 pi h bar, that are not close to 1. So they differ from 1 by at least h bar squared, for example. And c is actually a geometric constant. It's the area of, so if you look at the set of points theta A, if you recall, is the way we parameterized lines coming in from minus infinity. If you look at the area of theta A such that the classical trajectory that starts on the line with coordinates theta A, yeah, let's go back to this picture just to remind you. So here's the picture of theta A. So the area of theta A such that the classical trajectory starts on the line with coordinates theta A meets the interaction region where V is not zero. If you think about it, a lot of trajectories never meet the interaction region because the lines are far from the support of V. But some of them do, and we calculate the area, and that's C. And of this finite number of eigenvalues that are essentially different from 1, these are asymptotically evenly distributed around the unit circle. What that means is that if you look at some, I think it's best in a picture, if you look at any interval of the unit circle, you ask how many eigenvalues there are. Remember, we're doing this in the limit h bar goes to 0. Well, the number of eigenvalues is proportional to 1 over h bar and to the length of the interval, and the constant of proportionality is that constant c that we saw before. Oh, together with 4 pi squared. So asymptotically, that's the number of eigenvalues in that region. So although we're not able to pinpoint individual phase shifts and say that phase shift is approximately we can actually make a slightly weaker statement as the asymptotic number than any interval of the unit circle. And yeah, I think I'd better stop there to leave time for questions.
All right, thank you very much.
Yes, there is. Yes, yeah, really good question. Yeah, we have been looking at linear equations here in this lecture. And then the scattering matrix is a linear operator. And so we have all the formalism of linear operators like the spectrum and eigenvectors, eigenfunctions, and so on. But you can look at nonlinear scattering. In fact, when I first came to organize these lectures, I hoped to talk about nonlinear scattering, but soon came clear that was a bit ambitious in a single lecture. So I haven't talked about that. Yeah, in that case, Schrödinger's equation is a nonlinear equation, and you still have a scattering operator, but it's a nonlinear operator. So then we can't directly make statements like this because for a nonlinear operator, we don't really talk about eigenvectors and eigenvalues and so on. But it's a really interesting topic, and I mean, I could talk for hours about it, but yeah, there is nonlinear scattering.
Is this equidistribution result essentially like quantum unique ergodicity progress, or is this connection not that?
There's some sort of link. So it's not directly related to ergodicity or unique ergodicity, but yeah, that's a relatively technical question. It might be best if I talk to you after the lecture if you have any
I
time.
just know that it's about equidistribution of some sort of eigenvalue, so it seems very simple.
It's actually about equidistribution of the eigenfunction. So about these Fs. So if we ask what are the eigenfunctions and how do they distribute, then that's related to quantum unique ergodicity. In fact, we could make some statements not about unique ergodicity, but about quantum ergodicity in this case too.
There's a question online. You're also welcome to put it in the chat and we'll read it out.
I'm still not 100% sure what you mean when you say you're taking a paint constant to 0. Does that mean that the radius of support gets smaller in some sort of sense, or are we thinking more like time-wise and time taken for part of the travel through?
Yeah, well, firstly, as a mathematician, I'm quite entitled to take my Planck's constant to 0. So really what it means is that you're looking at a relatively macroscopic level. So, you know, you can't study a like single electron in a helium atom or something like that and apply the semi-classical limit. That would not be sensible, because then you've really got a fixed Planck's constant, which is quite large relative sort of length scales you want to look at. But the more you look at macroscopic objects and those sort of macroscopic length scales, the more Planck's constant is very small.
So this so the potential constant gets smoothed out in some sort of ways. I think the retention here, I guess if we think about it as like interchange in some bits and like graph, like as you zoom out further and further, it's kind of thing about it, it's more smooth down average.
Not exactly. I mean, there's a different mathematical procedure called homogenization, which does that. It looks at smoothing out rough potentials and then at different length scales, but that's not really what's going on here. Yeah.
All right, and was there a question online? So let me read the question online. Does this include the case when potential function is not continuous or even singular? Or do you have to generalize the theory to such potential functions? I think it's
so we've made a really big simplification that the potential, well, firstly, it's compactly supported, so that's a simplification. I mean, typically in physics, potentials do decay at infinity, but only at some rate. They don't actually drop off to 0. So that was one simplification. And another one is I implicitly assumed that V was somewhat smooth. But actually in physics, you have potentials like the Coulomb potential, which blows up at R = 0. So that's, the Coulomb potential is really the electrostatic potential between two charges of distance r, and that goes to infinity when r goes to 0. So there are mathematical difficulties in both cases, and they're under relatively active research, I would say, at the moment.
Well, very good questions there. We may have to end with one last question because in the interest of time, some people are going to lecture at 1:30. So maybe just one quick last question. If anyone of you wants to okay, maybe you go first.
So I think you might have mentioned this, but
So H is big in like with the scale of electrons, and the scale of variance. It's possible. In what sort of size range is semi-classical?
Well, semi-classical really refers to looking at the limit. So we're not looking at any particular value of H, but rather the sort of asymptotic statements we can make as H goes to 0. So with the interpretation that when H is very small, then these expansions will be accurate.
What's the difference?
Yeah, so the classical is what I talked about at first. It's really about point particles like marbles moving around in a phase space. And the semi-classical is looking at the quantum picture. So you are looking at a wave function and Schrödinger's equation. But you're looking at the asymptotics as H goes to 0, H bar goes to 0. And then there's a lot of links classical when you do that. That's why it's called semi-classical. It's the link between the quantum picture and the classical picture.
Okay, so with that, let's thank Andrew again.